Welcome to today's SMPTE Standards Update. The topic is the Lip Sync Challenge. I'm your host, Joel Welch, SMPTE's Director of Education. Welcome everybody. Hope everybody is safe and warm. It is snowing on the East Coast. Today's speaker is Mr. Paul Briscoe. Paul, are you there?
I am here. Can you hear me?
I can.
Good morning, good afternoon, good evening, everyone, wherever you may be. Thank you for joining us today. You can see my smiling face on the screen with us, not live, but I'm here in Toronto in the beautiful sunny winter weather. My name is Paul Briscoe, and I'd like to chat with you a little bit about the topic of lip sync today. As I push the button to see if I have control, I do. We're not talking about these sorts of kinds of lip sync. If you talk to most non-technical people, they're quite familiar with the idea of singing in the rain, or of course the litany of modern things that's led to. But we're not talking about that kind of lip sync. We're actually going to talk about this kind of lip sync, the kind that we're all familiar with, the technical issues associated with audio-video synchronization. So strictly what we're talking about is maintaining audio-video synchronization throughout the media ecosystem from acquisition to consumption. Bit of a big bill to try and fill. The acquisition part's pretty easy. We can build a rig, and put together a field kit, go out and shoot stuff, and have fair confidence in that equipment. The rest of it, though, everything downstream from there is where the problems tend to accumulate. So that's where we're going to focus. And as you'll see, the SMPTE Standards work we're doing in this area addresses the issue both right at the head end and all the way down through to consumption. So let's move on and talk a little bit about lip sync here. So what we're going to cover, we'll talk a little about the nature of the problem and some of the sources of AV sync errors. We'll talk about legacy solutions briefly and some candidate technologies that were looked at. And then the selected technology we call fingerprinting. We'll look at how that works and how we generate fingerprints from video and audio, how we actually attach that to the essence. And then we'll look at the system level and how it works in the system, and then a little recap of where we are in the standards activities. So the nature of the problem. Well, the problem is really quite a simple one. The sound and the picture are not aligned in time. You're watching the video and the audio is somehow not synchronized to it. The impact to the audience varies according to the content. If you're watching live music with a shot of the band and the drumstick hits the skin, you'd better hear the sound pretty reasonably close to the time you see it. The same goes for sports and the ball hitting the bat, crowd sounds, and so on. Of course, sound effects are frame accurate when the Foley artist puts them in, and dialogue, close-up dialogue of people talking is very, very important. That's the place, of course, it's most commonly observed. It's important to know it depends on what you can see. You do need motion and sound. If either one of those is absent, there is not a lip sync problem at that instant in time. This is one of the challenges of lip sync, is to put a system in place that can work when the data is available, and then we'll sit quietly and wait when the data to correct is not available. The interesting thing about the nature of the problem is the human sensitivity aspect of it. From birth, we're programmed to understand that sounds moves slower than light. Everything we experience in life is affected by this physical phenomenon. And if you visit the baseball park, you see the ball hit the bat, you don't hear the crack for a little while. That's programmed right into our brains at a very, very low level, right from birth. If, however, the sound arrives before the picture, this is quite unnatural. Your brain is not used to it. Your brain has no model to refer to. There's no natural phenomenon to have trained it. And this is something that raises a flag in the human brain. So there is a susceptibility problem if the sound comes before the picture. And there's a hysteresis effect as well. And this is just a human behavioral thing. In the words of my daughter, once you've seen it, it cannot be unseen. So once you notice a lip sync problem of a certain magnitude, you may continue to notice the problem even at a reduced degree of severity. What's the problem? Well, the problem is a diminished viewer experience. The whole point of our business is entertainment and information. It's to give people something they can sit and absorb. And if that viewer experience is diminished by any technical issue, well, we can do something about that. So aesthetic enjoyment and quality of experience are really what gets attacked by a lip sync problem. It's irritating. It's really annoying to watch. And it'll make people change the channel. quite often, or it'll make them pay less attention or completely ignore what's going on the screen. Now, if you're a sitcom, that's not so bad. If you're a commercial advertiser, that's not so good. Advertisers do not want people to not pay attention. Another problem is the loss of the viewer's suspension of disbelief. Possibly the reason you're watching the show in the first place was to become immersed, enjoy it, and disconnect a little from reality. And suddenly you're slapped in the face with something that catches your eye and takes your enjoyment away from the actual content you were watching. And perhaps most insidious of all is some data recently that indicates that there's a potential loss of believability of the content when lip sync error is occurring, possibly due to people's level of disconnection. But politicians and advertisers really don't like when the content isn't believable. The whole point of the content from the advertiser and the news point of view especially, and politicians too if you wish, is that the news be listened to and understood and believed. And it's more of a problem today than it's ever been. There's always been touch points in systems where we could get a handle on lip sync. Today's systems are big and complicated. We have content that's extremely rich, and we have less rigid shooting styles, in-your-face camera work, and so on, that gets lots of lip sync cues on the screen. And these screens are larger, they're higher resolution, so there's more lip sync cues available visually. Our system designs today are very complex, and they span huge geographies, global geographies, regional geographies, and these long complex paths can have uncorrected signal processing and physical delays in them that are that need to be corrected for in some cases and need to be considered in all cases to ensure that the audio and the video remain timed together. Compression, well, we all know compression never breaks. We use it all the time for storage and for transport. The reality is compression is pretty darn good, but you have to know what you're doing, and again, you have to make sure you manage your audio-video delays if they become differential in the system somehow. We have complex and multiple distribution architectures. This is a little different from what I was getting at with system designs. Distribution architectures are the way we get from the point of emission to the home, and there's many, many ways today. We'll talk about a couple later. But these are all fraught with potential problems. TV sets today are extremely complicated. This means there's delays inside while signal processing takes place. And then if people build a home theater with a separate receiver and a separate amplifier and all this nonsense, it's really getting quite out of control at the viewer end. Of course, the internet has raised the awareness and continues to raise the awareness of what lip sync and the lip sync problem is all about. Anybody who's watched internet video is well familiar with the level of disconnect we see there. And perhaps the biggest problem, at least in my mind today, is viewer awareness. More and more people are aware of the problem, possibly because of the internet and the other things we've talked about. But when viewers are aware of it, it's even worse because they know what they're looking at. Where can it creep in? Well, here's an example of a few little blocks, and you might wonder where lip sync errors could creep in. Well, let's assume the mobile truck actually has it together and it's built correctly and operated correctly, so AV comes out of it in time. But where else in the system can it break? Well, there's lots of places it can break between the beginning and the end. Even on the link to the studio, you can have a lip sync break in the compression domain, going through your infrastructure, going through your branding and processing, the output end of the station, output of the network, your link compressed to the local station, local processing in the station. You may even see errors in your off-air IRDs, your returns, your confidence feeds, even in your server. Depending on the technology you're using and what you're gluing together and how your system is built and qualified. So there's a lot of places in the system where this problem can creep in. The audio and video, for example, may travel on separate roads in life. These could be discrete audio-video signals in the system versus embedded audio, for example, in SDI. The audio-video may travel down different signal processing paths and through different processes with different delays over many different forms of transport with their own inherent delays. Of course, compression, encoding, and decoding is a big opportunity for errors if not correctly managed, as is storage. Human error, a vast opportunity to mess things up. Humans are wonderful at getting things done right and equally so at getting them done wrong if attention isn't paid. And it could be innocent. It could be simply from routing or patching around something, or it could be the QC operator snoozing, or simply missing what happened in that brief instant where they had the cues on the screen and in the speakers. And it can happen in multiple places en route to the consumption, right down to the viewer's set. And we all know that errors never average to the middle. It would be nice if they did, because if there were enough system errors, it would eventually come out in the middle. But of course, errors don't tend to do that. And these things tend to concatenate. Here's an example of a subtle contributor. In a system where you're pushing video from one end to the other, you may have 1 or 2 or 3 or more frame synchronization steps where this video is retimed to a local timing reference. So we fix our video timing by locking it to a new gen lock. This is good. The problem is we have a different timing domain on the input and output side of these things, so the delay going through the device varies up to the point of a frame, for example, as it's increasing delay, and then it jumps to no delay as it continues to manage the delay. And one frame sync in the past, such as FS1 in the drawing below, shows the behavior of this frame sync. Somewhere else in the system, we have a frame sync 2, and frame sync 2 is locked to another gen lock with a slightly different time base. And the net result is the bottom trace in that little graph. You can see a little sawtooth stepping up as frame sync 1 chugs along, and frame sync 2 adds more delay. And the little red circle around it there is a little peak as we just touch 2 frames delay before both of them drop to 0. That could be the trigger that causes the viewer to notice a lip sync problem. They hadn't noticed it before, but as of that trigger point, it caught their eye, and now they can't unsee it. So now, through subsequent material, they're watching for it, they're sensitive to it, and even when it could be well within tolerance, they may still be seeing an effect that they notice as a result of this peak. So typically, for example, frame synchronizers use tracking audio delays so that the audio going through the frame sync is sample rate converted to keep it in time with the video, and they predict the velocity and the direction of the frame drop or frame repeat so that when that happens, the audio is in precisely the right place that can occur. Now, what it means is there's a variable lip sync error, but the variability of the lip sync error is constrained to plus and minus half a frame. So by this means, that kind of an audio delay manages the lip sync. However, using just a regular audio path and then video frame syncs can result in this galloping cadence of lip sync. And it isn't just frame syncs. Vision mixers, production switchers, I think many people call them nowadays, contain DVEs. We do re-entry into them. When you re-enter with a DVE, you immediately throw a frame delay. If you're doing a multi-ended news conversation, for example, a multi-person interview with windows of people's faces, these can become delayed. Of course, when they're talking, people are looking at them, and their lips are perhaps in or out of sync, and then they look at the main announcers on the main window, and their lips are out or in, and so on. Routing switchers today have huge amounts of processing integrated directly into them. This is a potential problem if you're not aware it's there. Cameras won't even go there. There are so many types of camera technologies available today, and you pretty much have to trust the camera manufacturer to tell you the delay from optical light to electrical signal. And if that camera is not where you're getting your audio from, then you need to be considering that as well. Up-down cross conversion, format and frame rate conversion, all of this stuff takes time. And there's latency which is applied to the video path, which may or may not be matched in the audio path. Compression, it takes time on both ends. Compression systems need to be tightly integrated. There's a variability in the viewing environment, as I mentioned before, with home TV sets. Even in your system, you can end up with variability in your QC room viewing environments. System design, it's a big one. If you design the system wrong, of course, it'll break. And then a whole new one with a slightly bigger font, IP infrastructures. Will IP infrastructures be better, be worse? Well, we have no reason to think they'll be better by design, and we have no reason to think they'll be worse by technology, but we just need to wait and see. And it used to be really simple, right? After we broadcast a signal, there really wasn't much opportunity to break it. We sent the audio video up to the stick, and from there, it's microseconds to the home. The beam literally leaving, the scanning beam leaving the transmitter is literally tracing that beam on the screen at home a very, very tiny amount of time later. Today, our distribution ecosystem is a whole different story. Many, many codecs between the actor and the viewer, and multiple distributions, things like satellite cable, IP public internet, private internet, and so on. And then we have downstream value adds. We do things like commercial substitutions. We do logo and graphics insertion, often in the compressed domain. Here are places as well where we do visual augmentation. We need to make sure we touch the audio as well to ensure synchronization of the program content remains intact. And again, viewing environment variables, things like vendor choices. You can buy TV sets from more manufacturers probably than ever before in history. And there's set-top boxes, there's home theaters, there's media players, there's all this stuff downstream of us. It used to be really simple, and all of a sudden has gotten really complex. This is a slide from a study done in Europe. This is an examination of set-top boxes. So this is receiving a compressed stream over a couple of different technologies. These are the audio technologies that were looked at on the right. The video in this case was MPEG-2. And the delay from early, moving to the left on the chart, and late, moving to the right, and that's audio with respect to video, shows that as they tested these set-top boxes, they discovered there was a bit of a variability between manufacturers and models. And I've got no information here about manufacturers or models to protect the innocent. But as you can see, and this is in Europe, of course, where frames are slightly longer, but we have some delays out to the 100 and some odd milliseconds on the right and similar magnitude on the left. So these are all products available off the shelf. People all over the place have all these different products on their TV sets, and this is what they're experiencing from good synchronized audio video. This is the type of performance that's being seen downstream. So clearly there's issues even once the stuff leaves our hands, us being the broadcast domain. So why is it so bad? Well, there's a lack of standards for broadcasters. Measurement usually involves some human interaction, and human interaction can, in fact, be fallible. And it's a spot measurement, if at all. Nobody has somebody watching lip sync 24/7. And there is no single interoperable measurement method available to us today. And we really need this for something we can use in service, something we can use with live content. There's also a lack of standards for distributors and consumers. Now, they themselves don't need the standards, but the people who build their equipment do. The interesting thing is MPEG is where this all kind of starts in that domain, because MPEG encoding, as specified in ISO 13818, is normative. However, decoding is not. So you can build a perfect MPEG stream, and I can build a decoder which will decode it well, or I can build a decoder which will decode it poorly, and I'm not constrained as to which one I build. And when my customers don't complain, I'm going to watch the cost of my silicon a lot more than I'm going to watch the viewer if they're not complaining. Also, internet codecs and players exhibit extremely variable behavior. They've evolved up from clunky, chunky, multi-frame per second things to systems which now deliver beautiful pictures and beautiful video audio. But en route, anybody who's experienced is familiar with things like jerky video and bad lip sync and so on. And even if they fixed every internet media player today, the reputation would stick with them that they have a problem. So there's a lot of things that cause this to be really bad downstream. So today, let's talk a little about how we do our measurements of lip sync. The most common way we do these measurements is out of service. You take a path, you take a system chunk or a system element that is not in use, not on the air, and you do your measurements. And these are simple techniques. Some can be automated. There are a number of vendor solutions which can be automated. They can also be manual, the old deep flash lineup thing that people do with remotes and so on. It's actually relatively foolproof. At the time you use it, the instant you use that, say at acquisition, that's fine. Or in your system, you're measuring a path in the system that measures up fine. At that instant, you can trust your measurement. What you don't know is what's happened later, and it could be because of system design reasons, it could be because of system fluidity, but you won't know. It does require human involvement, which is annoying because we all want to try and staff optimally, and having somebody watch lip sync, a fallible measuring person watching lip sync is probably not a great thing. And we cannot use it within content, and we cannot use it on air. And that's a really important problem because we can use this to set up and test and qualify, and then we, from there on, have no idea. It's like setting up your studio with a scope and then taking the scope away. You keep running, and you just keep hoping. So for acquisition and editing and testing, this is fine. For general operations, not so much. So what we're looking at, moreover, is an in-service measurement technique, something we can use on air within content. On air doesn't necessarily mean transmitted, it means in live content. These are available today from various manufacturers. I'm sure I've jilted some with my little list on the right of some that just come off the top of my head. There are many who build this stuff. They use various techniques, many of them protected by patent. And these devices offer many varying capabilities, from very powerful and high-performing to maybe not so great. These are products in our industry. These are intended for use by us within broadcast plants and broadcast systems. These devices have varying degrees of complexity, and their effectiveness may not traverse all the processing that the media will encounter as it goes through life. These tend to be box or minimally a module level solution in a modular equipment platform. These are biggish kind of products. These are not small things. The bigger snags are the next two bullets. These products are non-interoperable among manufacturers. So if I go to the list on the right and I buy a box from the third person down in the list, I have to buy all my other boxes from that same third person down in that list if I want to implement a holistic system. If I buy a box from the fifth person down that list, that's great, but they will not play together nicely. This may be fine for many situations, but here we are at this point in the industry and it hasn't stuck. And one of the reasons is because you have to commit to one flavor or another. And this hinges on the bigger problem at the bottom, which is where SMPTE is now involved. There's really no standard to enable manufacturers to build stuff that will interoperate, and that's where we can help by developing such a standard. So the kind of capability we're looking for in our ability to measure lip sync is a standardized in-service measurement technique. Something that's standardized, I can pull the standard down, I can build a piece of equipment, and I know it's going to play with other gear, and it'll work on in-service content. Got to use it on the air with live content anytime. It needs to be medium agnostic. Don't really care what form the video is taking or how it's traveling around, and particularly how it's traveling around on what kind of transport. We want this to be agnostic of the medium. We'd like to find a low degree of complexity. We want something so simple and so cheap we could consider putting it on any port of any device. We could measure incoming lip sync. We could reestablish outgoing lip sync at a cost point that would not be prohibitive. So to move from a very expensive box or module solution to something that you stick on a BNC connector. We want interoperability among manufacturers. It's very important that people have the benefit, just like SDI and all of the other standards, the ability to build something to work at that standard and know that it's going to play nicely. We want this to work throughout the chain, anywhere in the path, not just in plant. We want to traverse all kinds of processing, even when that processing is concatenated. We're talking about spatial geometric conversion for up-down cross conversion, for example. We're talking about compression and decompression, perhaps using various codecs in the path, but we want this to traverse all the processing. And we would potentially like this to be usable right down at the viewer end. So we were looking for a technique that will work right on down into the home, should we find a path to get there. So a couple of candidate technologies that were distilled out of the investigation were watermarking and fingerprinting. Watermarking is a technology that inserts information into the essence. The information is typically invisible and inaudible, visually and audibly. It's coded through various complicated and often proprietary numeric techniques. And it takes some pretty complex processing often to generate this stuff and to extract it. It actually modifies the content. Watermarking takes the content and adds something to it that should not be seeable or should not be hearable. And that modified content containing these invisible watermarks may or may not survive all signal processing. That's a function of the type of watermark, and that's a function of the technology that's inserting it, removing it, and so on. It may also not coexist well with other watermarks. So if I put a lip sync watermark into my content, that's all well and fine, and someone downstream sticks in some ad tracking and some viewer tracking watermarks. They may conflict with each other. One may stomp on the other, and so on, such that the video ultimately gets so watermarked up you can no longer use the watermarks, and they may start to become visible and audible in the content. And they can be removed. If you know the technology that was used to insert the watermark, you can use the same technology to extract that watermark, rendering that content unmarked. The other technology that was looked at was fingerprinting. Fingerprinting is the measurement of specific properties of video and audio essence and coding those properties into some metadata for use downstream. So we don't touch the content. Instead, we observe the content and we jot down some interesting, unique things about that content and we send them off for use elsewhere. It can use simple processing to generate the fingerprints. It does not modify the content. And because we don't touch the content, well, we don't touch the content. The content is safe and unmodified. It can survive processing. including compression, including arc, and so on, because at any point in the path, we can take that video and audio and extract from it those same observable cues we were using at the head, and we can again make that metadata. So it can survive the processing by virtue of not being there in the first place. As long as the picture and sound is there, and as long as we pick the right cues, we can extract them from the picture and sound at any time and generate fingerprints. And we can't remove it. Again, it's not there. As long as you have the essence, you can apply the algorithms, extract the fingerprints from the essence. Well, I shouldn't say extract because it's going to make you think about watermarks, but observe and record the chosen artifacts from the essence. You don't actually need it to be in the essence. You simply take the essence at any given point and you extract these. And again, extract is the wrong word. You measure these. So the winning technology we chose was fingerprinting. The reason for this was that it didn't touch the audio video, and it was implementable at a price point that was pretty reasonable, we felt. And we had a proponent who had some experience in this, who brought this technology to the table. Our good friends at Miranda Technologies have been working with this for some time. What they brought forward looked like a pretty reasonable solution on which to base our standards work. And thus fingerprinting is the road we followed. Now, it's extremely robust stuff. It withstands all of these things, including up-down cross and encoding, decoding I talked about, audio level changes, up and down mixing and loudness control changes, insertion of logos, lower thirds, and other graphics, resizing and spatial format conversion, frame rate and temporal conversion, cropping, and even signal distortions due to filtering, low-pass filtering, edge enhancement, and so on. This is the kind of robustness that we want our fingerprint to be able to have. And the steps in fingerprinting are actually fairly simple. And we're going to go through a few drawings in a second here just to try and illustrate how this works, but the steps are really as they are listed out here. We take our video and audio and we generate a video and audio fingerprint from this content. Now, this content at the point of first fingerprinting needs to be assumed to be in sync. I guess there's something I have to confess to everyone. If your content has never been in sync, fingerprinting will not fix it. Fingerprinting will allow you to measure and allow you to maintain audio-video sync. It will not fix it if you don't know when it's ever been right. So to fingerprint, we take our in-sync audio and video, and perhaps this is right at field shooting or right in the remote studio or right in post or wherever, but we generate our audio-video fingerprints. And we take that fingerprint data and we make a little payload out of a little packet. I'd like to stay away from the word packet, but we take our little metadata payload, and we take our video and audio, we somehow deliver that to our endpoint or our midpoint or somewhere else, either as a stream or as a file. And along with it, we deliver the fingerprint metadata that we derived from it. At the point to which we deliver the video and audio, we generate audio and video fingerprints from it again. We now have two sets of fingerprints at that point. We have the known good audio and video fingerprints, and we now have the unknown local audio and video fingerprints. We now take these fingerprints and we correlate one of them, let's say the video, because we don't know how much delay has been going on in this path. We don't really know where anything is, but what we can do is run a little bit of correlation code and go looking for the same fingerprint in both of the videos, the upstream and the local. And when we find them, we know those two things are temporally the same. We then go and we look for the associated audio fingerprints. And we know they're going to be somewhere nearby the video fingerprints. And in fact, the upstream one should be right adjacent to the video fingerprint, and the downstream one may or may not be. So we go and we find it with the correlator. And we now know four things. We now know when the two video fingerprints happened, and we now know when the two audio fingerprints happened. And the difference in time between the downstream audio fingerprints, between the downstream video and audio fingerprints is the differential delay that is the lip sync error. And we can use that delay now to drive a display or to consider driving some correction. Show it to you.
Hey, Paul?
Way. Yes, Joel.
We do have a couple of questions. May I ask them?
Oh, I don't know. I guess if I'm allowed to go over time, then yeah, I'll put them in.
No. Just
sure,
quickly.
go ahead.
First question is from our guest David, and he has a comment and then a question, and I might paraphrase his question. let's see, you were talking about measurements at the customer's home. He states it's only going to work to the home if the consumer displays include technology to read the delay and automatically correct for it. I don't think many displays have implemented the SMPTE automated aspect ratio standards. Is there anything to indicate that they might adopt this this particular standard more than they did the other one?
That's a good question. AFD is getting more and more widely deployed at the receiver end. I guess it comes down to opportunity for improvement and weight of complaints. So for the moment, we don't have a standard, we don't have a system, and we're a couple of steps away from that because we need to do this upstream before it's usable downstream, plus we need downstream standards organizations to pick this up and find a way to deliver it to the home. Once that is in place, then the manufacturers of home equipment can look at using it to better feature their products. But right now, it seems the price point and screen size are the two big things, and how everything works in an integrated manner is kind of secondary to the TV set manufacturers, kind of sadly at least. So I don't have an indication, and I'm the wrong guy to ask because I'm not in the consumer products world. But again, we put this in place, and if it can make it to the home, then the gauntlet is dropped for them to pick up.
Okay. The second question is, you stated that fingerprinting cannot be removed. The guest asked, isn't it true that signal processing can change fingerprints?
Yes, that's correct. So the fingerprint, and we'll get into this in a bit here, the fingerprint algorithms we've chosen use specific measures of the video and audio which are intended to be minimally impacted by various processing, such as geometric scaling, such as level changes, loss of detail, and so on. So the, I guess, I mean, what I should point out is if you have 2 frames of video and the associated audio, that's not enough to do the fingerprinting job with. This is a slower moving process, which happens over a period of time. The correlation, the measurement and correlation. And there's also a confidence factor involved here where the receiving end has to decide how comfortable it is with the fingerprints it's receiving from its local extraction as compared to those upstream. So it's not a hard matching process. It's a little bit of more of a soft matching process. And we do know as you degrade the signal more and more and more, the matching becomes less confident. But the algorithms were chosen through experimental research by our proponent to withstand a vast amount of messing with picture, particularly picture. That's the hard one. Sound isn't so bad. And you'll see a little test drawing in a few slides of some testing that was done early in the SMPTE process, where the pictures were quite badly abused through the system, and it still managed to pull the fingerprints out. So while it's true that a modified picture will produce a different fingerprint, it will produce enough of the upstream fingerprint that it can be correlated.
Great. And thank you. I shall withhold questions until a little later.
Or maybe I should just be less verbose in answering them. Thanks, Joel. So here's a generalized view of the system. This is kind of your generalized, back of the napkin engineer drawing. In the middle is a cloudy-looking thing, and this is your, in this case, I'm saying content distribution network. This is an older drawing, by the way. You'll see the use of the word signature. We originally started out calling it signature and have changed the name to fingerprint, but really it's the same thing. And I wanted to use this drawing because it is quite concise. So this content distribution network in the middle could also be your television system. It could be the guts of a mobile truck. It could be your entire broadcasting campus. It could be your entire coast-to-coast network. This is the system that's going to ruin AV sync. And going into this system on the left, we have video and audio. And they're known to be in sync. They're coming off a server. It's a show you bought from a syndicator. You know it's good. You've checked it. QC looked at it. It's all good. So at the time you shove it into your system, you extract the video and audio fingerprint signatures from it. And we deliver those along with the essence into your system. And this system, this could be video and audio as streams. This could be video and audio as files. It goes into your system. At some point in your system, they are consumed. And at the point of consumption, they come out of this cloud, the video and audio, from upstream that was originally good, and the signature that came from there, the fingerprint of that video and audio. And you take that video and audio, which has now been messed with in ways you don't know, and you again extract the fingerprints, the signatures from that. And locally, at this downstream point, you compare, as I described before, the signatures. I have a little graphic coming up which helps that. And at this point, you're now measuring the lip sync error. And you can actually measure a couple of things. You can measure video delay with respect to the source. You can measure audio delay with respect to the source. But the thing we're really interested in is the difference between those two. So when we compare the signatures, the fingerprints, we get a measure of the error between audio and video. And we can use that now to do a couple of things. We can consider adjusting the audio-video timing at that point, then fixing it. Or we can simply use it to drive an indicator to tell us how much. Now, an interesting thing, by the way, on the right-hand side here where the audio and video are again in sync, we can now re-fingerprint this content and send it on out because we've now corrected it and it's the same as it was upstream. What we're doing in the standard is shown on this slide because I know I'll be asked, and the reasons we're not doing what's in the red I'll explain in a second. We are doing what's in green. The standard covers extracting the audio and video signatures and bundling them into a payload. We're also standardizing how to transport them and bind them to files. The two things we're not covering in the standard are the comparisons of the signatures, the correlation and comparison part, and anything to do with the measurement and the auto-correction part. The reason being we're developing a measurement standard. The measurement standard gives us the tool set, the Swiss Army knife, to allow us to measure these problems. Correlation can be done in so many ways and produce results of varying quality. And we felt this was something that belonged more in the competitive space than in the standard space. So the correlation, the standard does not touch, nor do we talk about the actual measurement in the product or the actual potential for autocorrection or how that may be accomplished. Here's a slightly different functional view. This is a different kind of back of the napkin drawing. If we look at our top drawing, we have audio and video, and we extract our fingerprints, our signatures, and we stick them together into this little signature bundle. At the bottom of the drawing, we have some unknown audio video, where again we extract audio and video signatures, and you can see now that they're offset in time. And we also have from upstream, this drawing calls it the sent-in AV sync signatures. And there's where we make our comparison. We make our audio comparison, we make our video comparison, and then we compare our delays. The reliability estimation is something actually we're not building into the standard. It's something that implementers can consider. It's more like the lock light on your input video. We don't standardize what makes the light turn green. That's up to the vendor. So the fingerprinting algorithms, and the intent is that they measure simple characteristics of change over time, from frame to frame, or field to field in the case of video, and from sample to sample in the case of digital audio. You'll see shortly how that works. They need to be cost-effective to implement. We cannot be running big digital signal processors. We cannot have vast FPGA logic commitments here or huge amounts of code running. These need to be simple. And they need to be tolerant of the essence processing, as I talked about. We also want to generate low data rates. This is metadata. It's meant to be small, and the intent of these algorithms is to generate a small amount of data which will get the job done. So let's have a look at the video fingerprinting algorithm. We use fields or frames, and you'll notice I got the capital on the wrong word there. It should be small f fields and big F frames for processing. So we use the entire video frame or field for processing. And we do simple horizontal downscaling of HD signals to SD. Simplify our logic a little bit, get our comparison down into a smaller domain. We don't need every pixel of the picture to measure change. We then establish a central window within the picture. We're interested in the central action. We're not really too concerned about what's going around the periphery of the picture, and that's also where everything gets added. So we might as well just stay away from that stuff anyway. We then measure 960 specific samples from within that window. And the samples, you'll see shortly, have been selected so that as we use different picture formats, these samples tend to fall in collocated spots. So when we downscale our HD picture to SD, and we then have an SD version of the HD program coming in, we still have a way to map the one picture onto the other to be sure we're establishing the same fingerprints. And then we compare it with samples from the prior field or frame. So we have the 960 samples from today's frame, and we have the 960 samples from the frame prior or the field prior, and we do a comparison. And we compare sample to sample, and we look at how many samples have changed value by more than 32. We then divide that by 4, because that result gives us a single byte, and that byte is the video fingerprint for that field or frame. So here's the pre-filtering. It's just a simple 3-tap FIR filter. We downscale HD to SD using these coefficients. We only do it horizontally. Lines are not a problem, but we have too many pixels, so we can simplify life. If it's interlaced, we use fields. If it's progressive, we use frames. Our windowing provides fixed coordinates for each standard. The idea being that scaled images will land on top of each other geometrically after we scale them. And we selected our start and end samples to stay away from all 4 picture edges. So we're picking 960 samples somewhere central in the picture. We do our motion detection by comparing the second previous. So now it's clear I lied before. We don't compare it to the previous. We actually go back 2. The reason for this is shown in the drawing on the screen. When we're converting from progressive to interlace, interlace to progressive, we have this field to frame mapping problem. And it's not really a problem, but it means that if we go 2 fields away in interlaced or 2 frames away in progressive, we'll find that we're comparing the same thing. So this is where we get our video comparison from. We take wide channel only data and we truncate it down to 8 bits. We don't need them all. 8 bits is plenty. And here we count our samples, which have changed by greater than 32. We divide it by 4, and then we get a byte. And that byte is the video fingerprint. So this is the operation of the video fingerprinting algorithm. Every video frame, we generate 1 byte. Audio fingerprinting, we use 48 kilohertz samples. Only 48 kilohertz samples. Any other sample rates are sample rate converted to 48K. The reason being that it's hard to find anything but a 48K sample rate in our industry, and it's really not worth the trouble of accommodating others in the standard. We truncate it down to 16 bits. We actually do an absolute value here, but I didn't bother mentioning that. And we generate then 2 things that we use for comparison. We generate a mean, which is a long time constant, and we generate an envelope value, a short time constant. You could maybe consider this if you wanted as one is a very slow-moving audio meter and one is a very fast-moving audio meter. And then on a sample-by-sample basis, we look at envelope and mean, and we make a bit. And we select that bit to be a 1 if the envelope is greater than the mean at the time of sampling, and we select a 0 if the envelope is less than the mean. And we accumulate 1s and 0s for the entire duration of a video frame. And then we apply it to a decimator to reduce the data volume. Let's have a look. I won't make you read the eye chart, and people are welcome to go away and look at the errors in the code, but it's intended to simply describe a simple FIR filter. And the coefficient for the FIR filter is a large coefficient, and it causes a local mean to be applied to the audio. We use the same structure of filter with a much shorter time constant to capture the audio envelope. So we're doing the same thing. It's a 1-tap FIR filter, and it produces a much faster moving output that tracks the envelope of the audio waveform. And then we compare envelope to mean on a sample-by-sample basis. And there's an example of what the envelope to mean may look like at an instant in time. It's unipolar. I mentioned we do an absolute value on it, but that's kind of neither here nor there, really. And what we end up with from this comparison is an output of bits at the sample rate. This is the 1 bit per sample we derive. So with 48 kilobits per second, we're going to generate these bits that tell us whether the envelope is climbed above or is falling below the mean. We then apply them to a little decimator loop. And the decimator loop uses a factor from a table based on the video frame rate to reduce the data rate to somewhere around 900 bits per second. And this is simply, this is a simplification to reduce the data to a point where we can transport it and it's nice and small but at the same time, it retains both the ability to get correlated and locked up quickly, and it gets us to around a millisecond of resolution. Now, what audio are we going to fingerprint? This is an interesting challenge because we have one picture. You might argue there's two in stereo, but really they're one picture. But in audio, we have a whole different story. We have multi-channel audio to consider. So for multi-channel audio, the decision was made we would downmix multi-channel to mono. The reason being it's all the same audio within that sound field. We can still fingerprint individual sound field channels if we so desire for whatever reason somebody may want. But a multi-channel sound mix is the sound that's associated with the picture. So mixing it down to mono for generating fingerprints is reasonable. Multi-track and multi-language audio is supported as well. We can support, in fact, up to 32 individual audio fingerprints from whatever source of audio down mixes individual channels, separate languages, and so on. We were talking about multi-track audio and lip sync in one of the meetings. Somebody said, yeah, but if the only language that's going to match the lips will be the language the lips are moving in, the other ones don't need to be synchronized. We scratched our heads a bit, and then we thought, well, there's two things there. One is that often they work really hard to make the lips kind of look like they are moving in time with the language that's actually being spoken. And the other thing is the sound field associated with the mix of the other language may still be the same background sound field as the primary language. So we support up to 32 audios, and it'll be a local operating practice by people as to what audio goes into what fingerprint, and that'll be based on their audio map and the audios they carry. So we get these fingerprints. We have to do something with them. So we bundle them together. One bundle per video frame, and this video frame bundle contains the video fingerprint, 1 byte, and it contains some number of fingerprints of audio. And that's a variable, because just like mapping 48K digital audio into 59 or 2997 video, there's a cadence of numbers on an ongoing basis as to how many samples go in the video frame, 1601, 1602, etc. with embedding. The same thing here. The number of bits you get out of your audio fingerprinting varies on an ongoing basis as it gallops along with the video cadence. So you have several bytes of audio depending on the frame rate, along with your video byte. We also in here contain, we have several items in the container for use downstream, such as the proto version for future compatibility. We have our fingerprints. We have a sequence count, because we aren't sure that stuff is going to arrive necessarily in order across all transports. We have some status bits just to indicate to the receiving end what's going on. We have a field called ID descriptor. This is the data bucket we've held on to and built into the standard for future use to associate the fingerprint by use of some ID descriptor external to us. And we have a checksum, because heaven knows all data transports in the world are error-free. Why would we not have a checksum? We're using the same container for all binding and transport applications. This is kind of important. The fingerprint bucket always looks the same, whether it's inside SDI or whether it's inside a file. The payload is the same. This means that we can get in between media very, very readily. We can come out of a file and we can generate an SDI stream, and that same payload can just come off the disk and go into the video. We don't have to take it apart and code a whole new bucket for that transport. So the transport and binding that we're covering, at least right now in the SMPTE work, is the same payload being delivered by different means over SDI VANC metadata, over an MPEG-2 transport stream, and over UDP, over IP packets. We're also considering how to bind this payload to files. It's the same metadata in all domains. Really easy to move in between. So this should be a fairly straightforward thing. And as it turns out, this is not so complicated. So for SDI, we simply carry this in ST291 VANC packets. These are just regular old VANC packets, like any other. They will have a unique and registered DID and SDID address, so that they can be found and extracted according to 291. And they're inherently bound to the essence. Because it's right inside the video transport, right beside the video and audio, it's stuck there. So for SDI transport, our binding is pretty straightforward. We think it's pretty much lossless and error-free. I won't ask for a show of hands because I can't see them, but hopefully everybody on the call realizes that SDI is not an error-free transport medium, which is one of the reasons we have a checksum. SDI is a error acceptable, and very, very low error rate transport medium, but it's by no means error-free. For transport over UDP/IP, we're simply taking the same payload and we're putting it inside a raw UDP packet. It's now indirectly bound to the essence. It could be bound, for example, by IP address in the system. It could be bound perhaps by the ID descriptor field that we've built in. But it will need to be reassociated with the receiver. It's not inside the same stream, obviously. It may be errored. It may be lossy. It may be out of order because it's now going across an IP network with unacknowledged packets. That's actually all okay, because enough packets will make it to the receiving end, hopefully. If, something on the order of 90% of them make it, then it can do its job. It doesn't need every packet, every frame to do its work. MPEG-2 transport, they'll be transported as private user data in the transport stream with a unique PID. Again, it's inherently bound to the essence like SDI, although not quite as directly. It'll be via the map tables that it's bound in this case, but it's going down the same hose with the essence, so it's tightly bound. Also essentially lossless and error-free, as much as MPEG transport streams are error-free, the same comment as for SDI. And then finally, we're looking at how to bind these things to files. We have a lot of files in the world. We have MXF files, which are in our domain, and because of that, we can do things fairly elegantly with MXF files, as elegant as things in MXF ever get. So we're looking at an MXF-specific method for binding fingerprints to MXF files. But then we have this problem that the world is full of everybody else's files. Why can't they all use MXF? So we have all these media files, and they only have one thing in common, and that is when you press play, video frames and audio come out of them. So we're looking as well at a method to create a binding of fingerprints to any kind of file. Doesn't matter what it is, as long as it plays out video and audio. That could be associated with the fingerprints from whence it came. So we're looking at how to do something file agnostic there. This work is under development, and you'll see when I get the status in a couple of minutes here where we're at. So for prototyping and testing such a thing, I mean, it's all great to dream this up and write it down and go ahead and publish a standard. Does it work? Well, our proponent, in fact, has spent a fair bit of time both in the lab as well as in the field with this technology. And for the purposes of this work, they have built a road kit, actual little shipping crate full of gear that can be shipped around. And it consists of a fingerprint encoding, I shouldn't say encoding, but a fingerprint source and a fingerprint receiver. And it was sent to several users with the instruction sheet that basically said, see if you can break it. And if you can, tell us how you broke it. We sent along a test plan, we sent along a results spreadsheet and all of this stuff. And the results were very, very successful. People did try to break it. They put it up to the satellite and down from the satellite and down to SDE and compressed it with this and screwed it around with that. And there were no particularly reasonable failure modes found. What do I mean by reasonable failure mode? Well, if the picture is acceptable and the sound is acceptable, the fingerprint should be extractable. And we had no cases whatsoever where the picture was viewable and the fingerprint was inaccessible. Here's an example of one of the tests that was done. I'm not going to walk this eye chart with you, nor am I going to force you to do it yourselves. It's just representative of one of the paths that was tested and the different equipment that was in that path and some of the test points. And in all cases of testing this configuration, everything worked just fine. So it just gives you a sense that we've taken this technology somewhere beyond a workbench and an oscilloscope to see if it actually does work. So on the SMPTE side, here's what we have on the go. We have an ad hoc group. It's a subgroup of the 24TB parent group called 24TB01 ad hoc group LipSync. We've been meeting weekly for a very long time. I am the most recent chair of the activity. It's been chaired in the past by others. And only recently, with the arrival of the fingerprinting technology and the momentum that came with that, have we been able to sort of reach velocity and get our work to congeal here. We have a very strong core group of subject matter experts. We can always use more. I plead and beg any chance I get, and I'll do it again here. Please, if you're interested, sign up to this group and join on and give us a hand. But I'll tell you where we're at right today. We are writing a document suite called SD2064. This was a multi-part document suite. The first two documents handle the core material, and that's the generation encapsulation of the fingerprint. and then binding of the fingerprint for transport over streams. This is the Part 1 and Part 2 document. The Part 3 document, and possibly a document beyond that, will relate to file binding, and we have not authored those documents as yet. The document status today is that Parts 1 and 2 are now complete committee drafts. They have been through pre-ballot review. Comments received have been incorporated, and the documents are now ready for formal committee draft balloting, which means we're on the ramp to a standard at this point. The Part 3 documents are now actively underway in the group, and we meet every Friday from 2 to 3:30 Eastern Time, and this is our current focus, is now getting the FCD ballot comments resolved when they come in and carrying on work on the file binding. So beyond SMPTE, and back to the question from earlier, after emission, then what? You can always answer the phone and say, as we've always said as broadcasters, it looks good leaving here. It must be your set. And it might be, in fact, true today. Because this method will work right down to the point of consumption. And it's cost-effective enough to endure the downstream price points that brings to the table. If this was an expensive technology, it'd be less likely. If it's a simple technology, it's going to be more likely to find its way into things at a lower price point. We may need additional binding and transport standards, because SMPTE standards kind of end at the end of the broadcast plant in many ways. MPEG can make it down to the home, that's one way, and there's lots of other ways as well. There may be standards required in those domains to ensure that we find transport methods for the fingerprint payload to get it down to the viewer. It may require standards in bodies such as the CEA and DVB. We have established liaisons with these groups, and we will be following this conversation further now that we have the Parts 1 and 2 documents getting close. We can also use this technology in a walled garden ecosystem, things like Netflix and YouTube and so on. I'll tell you a little Netflix story, for example. I now have, I guess, 5 devices in my life that can play Netflix, and they all do very, very well with lip sync to varying degrees. So, for example, I can watch Netflix on my Chromecast. Hope nobody from Google is on here. Lip sync's not very good on a Chromecast, guys. I can watch it on my WD player, and it's a lot better. So even within these walled gardens, they don't make things work right necessarily. And this is a technology that can wrap itself around any system and allow the problem to be fixed independently of the underlying system technology. The other neat thing is it can be added retrospectively and used anywhere. If you have a piece of content that's never been fingerprinted, but the audio and video sync is good, you can fingerprint that content at that instant in time. And going forward, you now have fingerprinted content. So where does it end? Well, maybe it all ends here. Maybe we've found the endpoint for lip sync. This standard offers a tool set to solve lip sync issues independently of underlying media systems and technologies. It's a wrapper solution that goes around stuff. Metadata from upstream essence is made available to downstream devices for a measurement and correction. A wrapper around the system. It really doesn't care what's going on inside. Just stick it on the ends and it does its job. And it can offer a self-healing system behavior. Combined with autocorrection, it offers the opportunity for systems to discover and repair lip sync errors invisibly to the viewer. So in conclusion, a standardized interoperable lip sync measurement system is coming soon to a signal near you, we hope. This will enable vendors to offer a broad range of lip sync measurement and correction capabilities across many devices at low cost. And if deployed end-to-end in the system, it can enable assured AV synchronization throughout. So we're really hopeful that this work will result in some of these grand ideas that may happen, but we certainly have the Swiss Army knife in hand and the tools to build these solutions. And we're really pleased that our committee is now at the point of being able to get the Parts 1 and Part 2 documents out, we hope very shortly, so that the industry can begin chewing on this stuff. And that's really all I had to say, Joel. Thank you all very, very much, and as much as Joel and time will allow, I'm happy to take questions.
Very good. Thank you, Paul. And we do have a couple of them, and I think you answered the first one here. Let's see. Can the standard be incorporated for user-generated content?
Sure. It doesn't really care what the content is. Again, excuse me. Again, it takes frames of video at some frame rate and samples of audio converted to 48 kilohertz And as long as you can provide that, it can generate fingerprints. So it doesn't really matter where the content comes from. This is what I meant when I said the retrospective thing. As long as you have in-sync video and audio, you can fingerprint it. And from there on, you can use the fingerprints to maintain the video-audio sync that was in place at the instant you established the fingerprints.
Okay. Here's a question. Are signatures the same as fingerprints? If not, why are two different words being used?
Very good question. They are identical and the same. Your presenter here was too lazy to touch the older drawing, which he thought was actually quite explanatory. And because I'm on a Mac, I don't have Visio at hand, and I couldn't change the words quickly. That's the reason. I apologize. They're intended to be exactly the same thing. The original word for fingerprint was signature. We just thought fingerprint was better. Reason being, fingerprint can also be a verb. So you can fingerprint the material as opposed to you can't signature the material. So it's a better word.
Okay. Let's see. Does the field data collection take into account the occasions where the intermediate processing gets the fields out of sequence when deinterlacing?
No. We decided, perhaps consciously or perhaps just as a matter of philosophy, not to build in hooks to work with bad video. Because if field order is swapped, your video is now garbage. I don't know the answer to how well it would work. It isn't designed to do so, but a simple field swap probably wouldn't cause the system to fail. The correlator may discover a lower level of confidence, but at the end of the day, I'm thinking aloud here, you can see me rolling my eyes up into my head. I think at the end of the day, it probably will still work. But if field order is swapped, your picture's garbage anyway, right?
Great. Let's see, this is a statement more than a question. One of our guests says, I would prefer if this could support multiple video sources that need to be in sync with a primary audio track. So that was just...
That's an interesting comment. Yeah, we had discussed that, whether multi-videos, multi-audios was something we wanted to undertake. And for the scope of work we were given by our parent committee and by the technology committees, that was out of scope. That said, the only thing that would be required to accommodate that would be augmenting the standard so that the payload could accommodate additional video payloads, video fingerprints in the payload, and additional audio fingerprints that would probably be necessitated by additional videos. So it's in no way precluded at this time, but it was out of scope for the work given to the committee. We'd probably be here another 5 years if that was in scope. Mm-hmm. But it should be fairly simple to do.
Good. We have just a couple more, or a few more questions here. Let's see. What happens at the consumer display if the audio played back, perhaps a second audio program, is different from the audio used for the lip sync measurement?
Well, it would never correlate. So if at any receiving point you have a video and then an unrelated audio, and you had fingerprints that came from different audio. So you have fingerprints, let's say, from the English track upstream, and then you locally generate Spanish fingerprints. As if there was no sonic similarity or coincidence between them, such as background or sound effects, there would be nothing to correlate. So they would never correlate, and the correlation part of the receiver would simply never, it would just say, I'm sorry, there's nothing to correlate.
Okay, next question. Who owns the fingerprint? The entity who generates it?
Well, here's the interesting thing. The fingerprint doesn't exist. The fingerprint is virtual, so nobody owns it. You can take a video frame and make a fingerprint from it. You can take a still picture and make a fingerprint from it. It's not very useful. But it's not an entity you can hold in your hand. It's something you can make from any image. So I don't really have a good answer to that question. I don't think anybody owns it because it doesn't exist, would be my opinion.
Okay. What about frame rate conversion? Will that have an impact?
So testing was done with frame rate conversion. This was brought home when I visited Australia a couple of years ago, and they said, you know, a vast amount of our garbage programming comes from North America in 59.94 or 29.97. They didn't say garbage, they said American television. But in any event, they expressed concern around this, so our proponent did some testing and discovered that correlation would still occur. What was happening in that case was that the correlation developed a cadence of confidence that was associated with the frame rate cadence. So if it was 25 versus 29, then there was a 5 hertz confidence cycle that was set up. And as the frames were identical when they aligned, the confidence would be very high. And in between the alignment points, when the frames were being interpolated, the confidence was reduced. However, the correlator could discover this, and the output of the correlator showed this very clearly, and it showed good correlation. It just showed that during the interpolated frames, the correlation was less. So it appears to work just fine across frame rate conversion, at least 25 to 29.
Okay, and the last question that we'll have time for today, could you please explain once again how fingerprinting will work when a chain contains a deinterlacer? It's because you'll have a signature per field first, and then a signature per frame. So
what we will have upstream is, so you're talking about a case, let's say, would this be a valid case where you have an interlaced signal upstream, and then downstream you've converted that to progressive, and you're pulling your fingerprints from the progressive frames downstream? So in that particular case, and I didn't state this clearly enough, in the case of video fields, we actually have 2 video fingerprints in the payload per video frame. So they're transmitted on a video frame basis, but if you're coding fields, then there are 2 fingerprints in that frame. So at the far end, you can still take a P frame that would be temporally associated with one of the I fields upstream, and you can correlate them. And your correlation factor will drop by a factor of 2, because of course you have half as many pixels, but again we're looking at big sort of fuzzy-ish chunks of the picture here. So the correlation going to and from progressive seems to be just fine. And the same going the other way. You have a P frame upstream, somewhere downstream you have an I field that temporally corresponds to that P frame. They'll still correlate very, very well.
Great. Well, that's all the time we have for questions. Thank you very much. Thank you, Paul, for putting together the presentation. And I hope that it wasn't too much work to do that. I do appreciate your participation in this. I know you're in the middle of your standards meetings as well. I'd like to thank our guests also for taking time out of their busy schedules. We will be taking this on this video and putting it on demand for on-demand playback on the SMPTE website, plus on YouTube. Thank you, Paul. And with that, we will talk to you next time, either on our SMPTE monthly educational webcast, which we have one next week on the All IT Media Facility, or on the next Standards Quarterly Update. Thank you, everybody.
Thank you, Joel.